Hello, everyone. Welcome to part one of a three-part series on PDL. PDL is PolyAnalyst proprietary language for accessing text in query format. We hope through this three-part series you'll be familiar with PDL enough to deploy it and use it to extract information, query on your documents, and perform all the natural language processing that you need. So, what is PDL? PDL stands for Pattern Definition Language. Like I said, it's proprietary to PolyAnalyst, so you won't find any resources outside of PolyAnalyst for this. It is designed to be sort of like SQL, but for text. So if you're familiar with SQL, it's a query language to look for documents or look for records in a database. So if there's a certain record or group of records that you like to look for, maybe they have a certain ID that you like to query on, or maybe there's a certain field or an attribute that you like to exist in the table that you want to pull out, you can write a SQL query, and that query will access this data for you. PDL is very similar to that, but it does not work on a database. It'll work on unstructured text data. The basic way we can do this is just look for words. And this is the first layer of a PDL query called lexicon. We can just look for words, and if they exist in our documents, we can pull those documents and report them. You might see similar features in other solutions that work like that. What makes PDL special, however, it has additional capabilities and more complicated linguistic functionality that you probably won't see in other solutions. These features include morphology, syntax, and semantics. And we'll see how we can cover these areas in PDL throughout the tutorial. So where is PDL actually used in PolyAnalyst? You can use it in search queries like we've been talking about so far. If you like to look for documents that match our query, we can construct it like that. We can also use PDL in what's called entity extraction to actually create objects inside of our documents to be used for additional queries or information compilation or fact extraction. And then we can also use PDL queries in taxonomies, which are ways of organizing and structuring our data into hierarchies. This is very useful for classifying our data. PDL is made of three main components: arguments, functions, and operators. Arguments are the building blocks of any PDL expression. They are the words or the symbols that we are interested in. Functions perform linguistic evaluation of the arguments we provide. They add utility to our query, and they are what access all of the linguistic areas that we talked about previously, like semantics and syntax. And then operators add Boolean logic and set operations to our queries. So let's take a look at the most basic form of a PDL query. Just one word. For example, broken. If we use broken as our query, we'll find any piece of text that contains that word. Has broken area on L-arm, the contract signed was broken. However, broken will also match some more interesting text in our query. So with episodes of breaking through sedation, defendant charged with breaking and entering. So we didn't look for the word breaking, we look for the word broken, yet breaking is matched by broken. This is that second layer of linguistic content we talked about, morphology. Words are related to other words because they're just kind of different forms of the same idea. The word break has other forms: broke, breaks, broken, and breaking. When we use all these words, we know it's referring to the same idea. The only thing different is the tense here, or if it's going to be past, we broke something. If we are going to break something, something has been broken. I am breaking something. There's different forms of the same word. So when we search in PolyAnalyst for a word, PolyAnalyst automatically performs what's called morphological expansion on that word. It'll look for all the other expansions of that word included in that query. So you don't need to write all of these down in your query. You can just look for one, and it'll find the rest. That saves you a good amount of time. However, what if you don't want to do this? What if you want to be very accurate and very specific in what you're looking for? If you only want to look for broken, and you don't want to include any of the expansions, you can include square brackets around your argument. In that case, the contract sign was broken, that will be matched, but with episodes of breaking through sedation, that will not be matched because broken is not present. You have suppressed the morphological expansion. So let's talk about functions. There are different types of functions. One of the more basic ideas is the lexical function. Lexical functions modify the words themselves and modify the scope of the word. So here's some examples of lexical functions: form, stem, lemma, and Singleroot. Form will look for an exact match. It's very similar to using the square brackets. In fact, it's the same thing. Stem expands all forms. Currently, stem is an obsolete function. If you have an older version of PolyAnalyst, you might be required to use stem. However, in the newer versions of PolyAnalyst, this is automatically performed, and you do not need to use this function. Newer ideas are lemma and Singleroot. Lemma is based on what's called a morphological dictionary. It only matches the forms of the given lemma. The argument has to be in a lemma format. Singleroot is like using stem, or just looking for the regular word in the newer version of PolyAnalyst. But it has additional capabilities. We'll see some examples of these in a second. So, form, as an example, we have help, helped, helping, helpings, helps, and help. These are all forms of the word help. If we look for form helping, what will we find? We'll only find helping. Remember that form suppresses the morphological expansion, so we won't find any others. We'll find only exactly what we look for. If we look for stem helped, what will we find? We'll find all of these. Remember, stem, you don't need to do that anymore. It's just looking for the word and all the morphological expansions of that word. So if I look for help, helped, or helpings, they will all find the same words. Now let's take a look at two new cases. Lemma. What will happen if I look for lemma help? It will find helped, helping, helps, and help. Why is helpings missing? Well, helpings is a noun. I had many helpings of cake. It's a form of the word helping, which is also a noun. I had a helping of cake. But helping could be a noun or a verb. A helping of cake, or I am helping my sister get some cake. Depending on the context of the word, it could be a noun or a verb. When I search for the lemma help is a verb, and all of the direct forms of that word are verbs. So if I use the lemma function, I'm only looking at the direct forms of that word, so I'm restricting it to verbs. Helpings is not directly related to help in the lemma format. And so lemma is a little bit more of a restricted version of our morphological expansion. We only look for the directly related words. Now what happens if I look for the lemma helping? If I look for the lemma helping, I will not get anything other than helping and helpings, because once again, I need to keep the form the same. Helping in this context is a noun. The lemma helping is a noun. So it only finds noun versions. The lemma is the basic form of the word. And so the function lemma requires the base form of the word and we'll only look for direct descendants of that form. So what happens if I look for the lemma helpings? I'll find nothing, because there is no lemma helpings. Helpings is a form of the lemma helping. So if I want to use helping in a lemma function and find all the children of helping, I need to make sure I need to use the actual lemma helping instead of helpings. What about Singleroot? If I use Singleroot help, what will I find? I'll find all of these, and actually I'll find some extras. Unhelpful, helpfully, helpless. What Singleroot does is an additional step. Performs a stemming algorithm and figures out what the stem of the word is. And then it goes out to other words in the dictionary, stems those words, and as long as they have the same stem, it'll match them. So unhelpful has a stem help, helpfully, helpless, they also have the stem help. And so if I use Singleroot help, those words will be matched as well. So Singleroot boosts morphological expansion and actually goes beyond it. We can do some additional interesting things as well. We don't need to look for the word directly. We can actually add some additional information in our query. So we can add an argument called verb or noun or any other types of part of speech when we are using these words. And it'll only find that word if it's matching that type of speech. So for example, lemma verb help. It'll only look for help in the descendants of help that are verbs. The same goes for other parts. I don't need to give it a word. I could just give it a part of speech. If I want to look for any noun, I can look for lemma noun, stem noun, form noun, or part of speech noun. All these functions in this instance are equivalent. Here's some examples. I can look for things where he has eaten apples. I can look for nouns or verbs. So if I do lemma noun, and then I add a bar to indicate the or, and then verb, it'll match all the nouns and the verbs in that sentence. There are many different attributes I could add to this. So for example, if I like to look for plural nouns, I can use underscore plural to modify the noun and only find plural nouns. I can add more. If I want to look for verbs that are also past participles, I can add two attributes, past and participle to verb, and get eaten. And then it does not matter what order I add these. If I look for third person, masculine, pronoun, in any order of this, in this case, I can go on and find he. There are many different attributes, and you do not need to memorize these. In fact, I don't advise you to memorize these. Please refer to our help manual, and it will give you an entire list of these attributes for you to figure out which ones you want to use in different scenarios. If you remember that you need to use one, but you don't know exactly what it's called, just refer to the help manual, and you'll be able to find a list of these. So we've seen some lexical functions. Let's move on to some different types of functions. So what if we want to find words as they are related to each other? For example, near, sentence, follow, and phrase. Near will look for words that are close to one another. Sentence will look for words within the same sentence. Follow looks for words in a given ordering. And then phrase combines these together. It needs to be in the same sentence, it needs to follow it in a given ordering, and they need to be within a certain distance of one another. These are called proximity functions. So let's take a look at the first one, near. We're looking for near 3 red dog house. This will match the dog house is red. We have a red dog house, but it will not match our red brick house has a dog in the yard. Why not? Well, we gave it 3 words to look for, red, dog, and house. They have to be close to each other. Well, how close? The first parameter we give, the green 3, is an argument that indicates how close they have to be to one another. So we can see here, dog and red are within that distance, red and house are within that distance, and red and dog in the final sentence is not within the specified distance. Notice how distance is being measured. It's between the first word found and the last word found. That is what we're measuring by that 3 there. If we bump that 3 up to a 5, however, now we can match that last sentence because we've increased the distance between the first and last word. And now we can capture our red brick house has a dog in the yard. However, we can alternate which type of distance we are measuring. If I don't specify anything, the default will look for the distance between the first and last word. But if I specify a type of distance, for example, max gap, I then can look for a different type of distance. So max gap will look for the distance between any 2 words in the query along along the sentence. So dog and house, house is red. So dog house, house is red. Those are within 3 of each other sequentially, so we're fine. We have a red dog house. Again, any 2 words along that sentence are within 2 or within 3, so the query matches. And then our red brick house has a dog. Once more, we're good. Red brick house, within 3. House has a dog, again within 3, so we're okay. The sentence function is a very simple function. It just looks to make sure 2 words are within the same sentence. Dog house is red. The dog likes to run through the house. However, our house is large, period. A dog is in the yard. They aren't in the same sentence, so they won't be matched. However, I can include another parameter here. This 2 parameter will make the number of sentences apart expand. So now they can be within 2 sentences of one another. So our house is large, but then a dog is in the yard. That's the next sentence. So they're in 2 sentences of one another. So that query will be matched here. The follow function imposes ordering on our words. The dog house is red. Dog comes before house, so this is matched. The dog likes to run through the house. Again, dog is before house, so we're okay. However, our house is large. A dog is in the yard. Dog does not come before a house here, so this query is not matched. If we do the opposite, follow house dog, queries will reverse. The first 2 will no longer match because the ordering isn't satisfied. The last one will match. Notice we didn't impose any restrictions on them being in the same sentence or being close to another with any number of words. It just makes sure that at some point in the text, dog comes after the word house. Phrase dog house imposes everything we have seen so far. They must be within the same sentence. They must be in the order provided, and they must be within some distance. If no distance is provided here, in this case, they have to be immediately following. So the dog house is red. The dog likes to run through the house. Our house is large. If we impose extra distance here, we can increase that. And we can add more words here. Dog, run, house. So if we include the word run here, then it has to be between dog and house. Notice we could actually restrict this a little bit. Dog, run, and house all are within 3 of each other. Recall that near, the default argument was between the first and the last word. With the phrase function, the default argument is the sequential ordering, similar to max gap. So in this case, the dog likes to run through the house. So those are within 3 of each other sequentially, so we are okay. That's an important distinction to recall. The default proximity argument are going to be different between near and phrase. Depending on which of these functions you're going to be using, you need to recall the type of proximity argument they take by default. Let's move on to operators. And let's start with Boolean operators. The first is AND. This is a simple Boolean operation that you're probably familiar with. This makes 2 queries join together, and it just makes sure that they're both matched. So if we look for dog, and here's a new function called case, we take an argument called upper, so this looks for things in uppercase. So dog in case upper looks for a document that contains the word dog and something in uppercase. So they like dogs, like is in uppercase there, and there's the word dog, so this is matched. They have dogs, there is dog, and in fact the thing that's in uppercase is dogs, so this is matched. But the last query is not matched because while there is dogs, there is not something in uppercase. We also have OR. We can use operators inside of functions. So phrase have or like will match they like dogs. It will also match they have dogs. It will not match they sell dogs because sell is not have or like. We can use the not operator to denote exceptions. So not sell, we'll look for anything that doesn't contain the word sell. I can also use the not operator inside of functions. So phrase they, not have, we'll look for things that say they followed by anything that's not have. So they like, they have, they sell. In this case, they have, well, that's not what we want, so that won't be matched. So here's an interesting idea. What if we want to use dog to, what if we want to use this not to kind of add a filter on our query? So we want to look for something that's dog and not case upper. So in the first case, they like dogs. Okay, that's great. We have dogs, but we also have something that's upper, so this won't be matched. The second case, we have dogs, and we have something that's in uppercase, so this won't be matched. And then they sell dogs. Well, we have dogs, and nothing is uppercase, so this will be matched. But what if we want to specify that we don't want dogs to be uppercase? So how do we get the right-hand side? We want they like dogs to match because dogs exists, and it's not in uppercase, but we don't want the second to be matched. How do we do this? This is where the second type of operator comes in, the set operator. Set operators are going to restrict arguments and restrict functions. So we have to, the ampersand, and the slash. If we do dog and case upper, this forces the case upper to modify the dog. So if dog matches something, then the case upper has to match it as well. So they have dogs. Dogs is uppercase. It's dog and it's uppercase, so that's matched. However, I want to use it as a filter. So dogs, but not case upper. I will get they like dogs and they sell dogs, but they have dogs will not be matched because dogs is uppercase. We can use this to exclude things. We can also use a different function called except to exclude things. Except will look for anything that isn't something. It has to be something there. So except case upper will look for anything that's not uppercase. In this scenario, we have many things that aren't uppercase. They is not in uppercase. That'll be matched. They again is not in uppercase. And they is not in uppercase. As long as it finds something that's not uppercase, it'll be matched. If I want to look for they followed by anything other than have, that's great. They like dogs, so that'll be matched. They sell dogs, that's going to be matched. But they have dogs, so will not be matched. Take a look at some of these ideas. So anything that is not uppercase, we've seen this. Dog and not case upper. This will not be matched because there's dog, but there is something that's uppercase. Dog, however, dog / case upper, this will be matched because dog is not the thing that's uppercase. And then dog and case upper won't be matched because dog is not the thing that's being matched here. So here's some differences between not, except, and the set operators. Here's an interesting scenario here. What if I have phrase dog, not cat? This will be matched because all of these dogs, well, none of these dogs are followed by the word cat. These will all be matched by this query. What about phrase dog except cat? It's very similar, and you might think they're the same, but in fact they're not. In this case, none of these queries will be matched because except requires something to be matched. Not doesn't care. Not can say anything or nothing at all. Except requires there to be some word matched. It just can't be cat. That's a subtle difference between not and except that you have to keep in mind. Sometimes you can use a union operator. This is like or, but it is an upper slash. So cat or dog versus cat bar dog, those are the same thing. I can conjoin arguments with this, so case upper or lower dog, but I can't use case upper or lower dog. If you want to join arguments together, for example with case, you need to use a bar. Our operators follow an order of operations. So the order will be the set and versus the set not, the set bar, then the Boolean not, the Boolean and then finally the Boolean or XOR. If this is too much to memorize, just make sure you use heavy use of parentheses. You can put parentheses around parts of your query to make it a little bit easier to read and understand. So if I have not dog or like and case upper, if I don't remember which order these things are going to go into and I want to be sure I'm right in what I'm capturing, I can just use parentheses. So in this case it'll be not dog or like and case upper. So all of these are the same. They'll match the same thing. But this one at the bottom is probably easier to read, write, and understand. If you'd like to practice, find records which indicate the engine light was on. Think of how to construct a PDL query for this, and in the next video we'll come back and discuss how we might write this. In the next video, we'll start off with word class dictionaries and learn more about PDL. Thank you for joining us, and we'll see you next time.